In our everyday language, we often use the words mass and weight as if they mean the exact same thing. When you stand on a bathroom scale, you might say you are weighing yourself to find your mass. While this is common, in the world of physics, these two concepts are wonderfully distinct and describe very different things. Understanding this difference is one of the first great steps into seeing the universe as a physicist does. It unlocks a deeper appreciation for the forces that govern everything, from the apple falling from a tree to the majestic dance of the planets around the sun. Mass is about the stuff you are made of, while weight is about a force pulling on that stuff. Let's begin by thinking about what you are made of. You are made of atoms and molecules, a huge collection of tiny particles. Mass is simply the measure of how much of this stuff or matter is inside an object. It's a measure of your substance. Imagine you have a bag of sugar. The mass of that sugar is the total amount of all the tiny sugar crystals packed into the bag. It doesn't matter where you take that bag of sugar, to the top of a mountain or even to another planet, the amount of sugar inside it remains unchanged. Therefore, mass is an intrinsic property of an object. It is constant and unchanging, no matter its location in the vastness of space. Weight, on the other hand, is not about the amount of stuff. Weight is a force. Specifically, it is the force of gravity pulling on an object's mass. Every object with mass exerts a gravitational pull on every other object with mass. The bigger the object, the stronger its gravitational pull. The Earth is enormous, so it exerts a significant gravitational force on everything near its surface, pulling it all towards its center. This pull is what we feel as weight. It is the reason we stay firmly on the ground and why things fall when we drop them. So when you stand on a scale, it is actually measuring the downward force your body exerts due to Earth's gravity. So here is the core idea to hold on to as we explore this further. Mass is the quantity of matter in an object, a fundamental property that never changes. Think of it as a count of your atoms. Weight is the gravitational force exerted on that mass, a value that can change dramatically depending on where you are in the universe. One is a measure of substance, the other is a measure of a pull. This simple yet profound distinction is key. It helps us understand why an astronaut can leap great heights on the moon, yet has the same amount of stuff in their body as they did back on Earth. We are about to delve into this fascinating cosmic reality. Let's look more closely at mass. The scientific unit for mass is the kilogram, often written as kg. When you buy a 1 kilogram bag of rice from the supermarket, you are buying a specific amount of matter. This quantity is a fundamental property of the rice. If you were to take that bag of rice and fly it to the International Space Station, where astronauts float around in apparent weightlessness, the amount of rice in the bag would still be exactly 1 kilogram. The number of rice grains hasn't changed, and the matter they are made of hasn't vanished. Its mass is constant, a reliable and unchanging companion on any cosmic journey. Another important aspect of mass is its connection to inertia. Inertia is an object's resistance to a change in its state of motion. In simpler terms, it's how difficult it is to get an object to start moving, or to stop it or change its direction once it is moving. An object with more mass has more inertia. Imagine trying to push a bicycle compared to trying to push a car. The car has much more mass, and therefore it has much more inertia. It is significantly harder to get the car moving from a standstill. This property of inertia is tied directly to mass, not weight, and it exists even in the weightless environment of space. An astronaut floating in space might feel weightless, but their mass is still there. If another astronaut tried to push them, they would still have to exert a force to get them moving. The astronaut with the larger mass would be harder to push and, once moving, harder to stop. This is a direct experience of inertia in action, completely independent of gravity's pull. This is why a massive drifting asteroid in deep space would be incredibly dangerous. Even though it is weightless, its enormous mass and inertia mean it would require an immense force to change its path, making it a formidable object to encounter. So when we think of mass, we should think of two key things. First, it is the measure of the amount of matter in an object, measured in kilograms, and this value is constant everywhere. Second, it is the measure of an object's inertia, or its resistance to changes in motion. Whether you are on Earth, Mars, or floating in the void between galaxies, your mass remains the same. It is a fundamental part of what you are. It is the solid, dependable quantity that defines the stuff of you, regardless of the forces acting upon it. This unchangeable nature is what makes it so different from its partner concept, weight. Now, let's turn our attention to weight. As we've established, weight is a force. In physics, all forces are measured in a unit called the Newton, named after the brilliant scientist Sir Isaac Newton, and its symbol is N. So while you might measure your mass in kilograms, your weight should correctly be measured in newtons. When a scale shows your weight in kilograms, it's actually doing a clever little calculation behind the scenes. It measures the force you exert on it in newtons and then divides by the strength of Earth's gravity to give you the number you are more familiar with, your mass. The strength of this gravitational pull is not the same everywhere. It depends on the mass of the planet or moon you are standing on and your distance from its center. Earth, being a large and massive planet, has a relatively strong gravitational field. We call this the gravitational field strength, and on the surface of the Earth, it has an approximate value of 10 newtons per kilogram, or 10 N per kilogram. This means that for every kilogram of mass an object has, the Earth pulls on it with a force of 10 newtons. This value is the key that connects the constant nature of mass to the variable nature of weight. This relationship gives us a very simple and powerful formula. Weight equals mass times gravitational field strength. In symbols, this is written as W equals m times g. Let's use it. If a student has a mass of 50 kilograms, we can calculate their weight on Earth very easily. We take their mass, m equals 50 kilograms, and multiply it by Earth's gravitational field strength. G is about 10 N per kilogram. So, weight equals 50 kilograms times 10 N per kilogram, which is 500 newtons. This means the Earth is pulling the student downwards with a force of 500 newtons. Every object you see around you, from your pen to your school bag, has a weight in newtons that can be calculated in this way. This dependence on gravitational field strength is precisely why weight is not a constant property of an object. If you could travel to another planet, the value of G would be different. On a more massive planet like Jupiter, G is much larger, so your weight would be much greater. You would feel incredibly heavy. On a less massive body like our moon, G is much smaller. This is why your weight changes depending on your location in the universe, even though the amount of matter that makes you up, your mass, remains stubbornly the same. Weight is a story of a relationship, a gravitational dance between your mass and the celestial body you are on. Let's solidify these ideas with a classic example. An astronaut on a journey to the moon. Imagine our astronaut has a mass of 70 kilograms. Here on Earth, where the gravitational field strength, G, is about 10 N per kilogram, her weight is straightforward to calculate. Using our formula, W equals m times g, we find her weight is 70 kilograms times 10 N per kilogram, which is 700 newtons. This is the force that keeps her feet on the ground. Her body, her spacesuit, and all her equipment have a mass that is being pulled towards the Earth's center with a considerable force. This is her reality on her home planet. Now she travels through space and lands on the moon. The moon is much smaller and has far less mass than the Earth. Consequently, its gravitational field strength is much weaker, only about 1.6 N per kilogram. This is roughly 1/6 of the Earth's value. The crucial point here is that the astronaut herself has not changed. She did not leave any of her atoms behind. Her mass is still and will always be 70 kilograms. The amount of stuff she is made of remains constant. Her inertia is the same. She would still be just as hard to push or stop in a straight line. However, her weight on the moon will be dramatically different. We use the same formula, W equals m times g, but this time we use the moon's value for g. Her new weight is 70 kilograms times 1.6 N per kilogram, which is 112 newtons. Compare that to her 700 Newton weight on Earth. On the moon, the gravitational force pulling on her is only about 1/6 of what she is used to. This is why we see footage of astronauts bouncing and taking giant leaps across the lunar surface. It's not because they suddenly became lighter in terms of mass, but because the force holding them down, their weight, is so much less. In conclusion, the distinction is clear and simple. Mass is the measure of matter, it is constant, and it is measured in kilograms. It is an intrinsic property of you. Weight is the force of gravity acting on that mass. It changes with location, and it is measured in newtons. An object has the same mass on Earth and on the moon, but its weight is far less on the moon. So, the next time you step on a scale, you can smile, knowing that while the scale might be telling you your mass, you understand the deeper physics behind the force it is actually measuring, the persistent, wonderful pull of the earth.